All right, for the next installment of radiation, I'm going to deal with a couple applications of the radiation networks we saw last class. So two cases, infinite parallel surfaces, and the other case is radiation shields. So for infinite parallel surfaces, you can have a few different geometries. Most common is infinite parallel plates, so rectangular, really big plates. Last class, we derived this relationship between two objects, sigma T1 to the fourth minus T2 to the fourth, so that's your total power generated, EV. And then on the bottom, we have these resistances, 1 minus epsilon 1 over epsilon 1 A1. That's the resistance to actually make it off the surface. 1 over A1 F12, so to make it from surface 1 to surface 2. And then 1 minus epsilon 2 over epsilon 2 A2. That's that to actually get absorbed into the second surface. So that's my total overall heat transfer between my two objects. Now, if I have infinite parallel plates, these guys are infinite. That means they're really big. They're really big. That means their area is really big. Basically, A1 equals A2, both infinite. So I'm just going to call that A. And then F12 is essentially equal to 1 because these guys are infinite. That's all you're going to see. So if I have a plate here and a plate here, and I'm looking from one plate to the other, because the other plate's infinite, there's no way I can see around him. So the entire thing, that view factor equals 1. So all the energy being radiated off one of the surfaces is going to hit the other one. There's no way to get around it. So what we can do is we can simplify this equation a little bit because, again, my A's are the same. A1 equals A2. I know that F12 is 1. And so I can pull that A out, pull it to the other side. So Q over A, energy flux, sigma T1 to the fourth minus T2 to the fourth. Then have 1 over epsilon 1, 1 minus epsilon 1 over epsilon 1. The second term here just ends up being 1 because, again, the A is taken out. F is just 1, so that's just a 1. And then 1 minus epsilon 2 over epsilon 2. I can clean that up a little bit. So 1 minus epsilon 1, expand that out. I have 1 over epsilon 1. Epsilon 1 over 1 is just 1. Same thing happens here. So I end up with 1 over epsilon 1 plus 1 over epsilon 2 minus 1. So I have a minus 1 plus 1 and another minus 1. So overall minus 1. So easier formula for this particular case. So that's my rectangular infinite surfaces. I can also have a very long concentric cylinder. So again, an infinite cylinder in the sense that it's infinitely long. So I'm still going to have F12. So I still look at anything coming off of surface 1 is basically going to hit surface 2. And that's, again, assuming this thing's infinitely long. So if it's infinitely long, nothing happens at the end because technically this surface I can emit straight up. I can also emit outwards. But again, because it's infinite, this surface isn't really here. It's way too long. So basically I'm in the inside here, and anything coming off is hitting the second cylinder. So F12 is still 1. Again, it's basically approximately 1. If it was actually infinite, it would be 1. But again, nothing in real life is really infinite. So if this thing is really, really long, I can approximate it as being close enough to 1. The problem here is that my two areas are not the same because you can see that the radius or diameter of what I'm calling surface 1, the inner cylinder, is obviously smaller than the diameter of surface 2. And so area 2 is going to be bigger than area 1. What that means for this basically is that F12 equals 1, but F21 does not equal 1. And that's because I'm looking at this surface. Again, if I come down, I'm going to hit here, but I can come down at an angle and miss the inner surface and basically hit myself. So that's why F21 is not equal to 1, even though F12 is. So my equation gets a little trickier because, again, I have A1 and A2 in it. So I'm not going to pull the A to the other side like I did before. I'll leave it over here. And so I have sigma A1 T1 to the fourth minus T2 to the fourth, 1 over epsilon 1. So that still reduces to the same factor we had before. But then I have A1 over A2, 1 over epsilon 2 minus 1. So again, I have this factor of A1 over A2 additionally. The other geometry we deal with a lot is the sphere, and similarly for concentric spheres, basically same example or same expression. Only difference here is that I kind of split it up into, instead of areas, I have the radii, because area for a sphere, 4 pi r squared. 4 pi is going to cancel out, so just have the area as R1 squared over R2 squared. Other than that, exact same equation. Last case we can have is a convex object completely enclosed by a very large surface. So we've kind of seen an example of this where I have an object that's in a very large room. So the room encapsulates the entire object. And so in that case, my view factor again will be 1. And so all I have is sigma A1 epsilon 1 T1 to the 4th minus T2 to the 4th. A little bit of a summary on page 623 of the textbook of some of these geometries and the equations used. So that is infinite surfaces. The other thing we want to deal with today is radiation shields. So if you want to reduce the radiation heat transfer, one thing you can do is use materials that are highly reflective. So remember, anytime I have heat radiation coming in, hitting an object, some of it gets absorbed, some of it gets reflected. Technically, some of it gets transmitted, but we're still ignoring that part of it. So if I have very high reflectivity, that means not much being absorbed. So that's going to reduce any sort of heat transfer. The other thing I can do is use a shield between the two objects. So the shield's not anything fancy, it's just put an object here. And again, the more reflective this object in the middle is, the better, as we're going to see when we do the example. But as long as I just put an object here, it doesn't even really matter what it is, that's going to reduce the overall heat transfer. It basically adds more thermal resistance, because for this system that we have right now, it's just two objects. I need to make it off the surface. I need to see surface 2. So I have one resistance coming off the surface, another resistance to make it to the second surface, then a third resistance to get inside that surface. So I just have this equation. So again, I'm assuming I have two infinite parallel sheets, so I have a slightly easier equation than we had before. If I come along and add another object in the middle, now in terms of my resistances, I need to make it off of surface 1, and then I need to make it to surface 2, need to be absorbed into surface 2 on one side, and then I need to make it off of surface 2 on the other side, and then see surface 2 from there, and then be absorbed into surface 2. So I have this additional resistances of coming in and being emitted from the other side. So additional resistance from the shield here that I'm calling S. I also know that the overall heat has to stay constant, so I'm not going to be losing any energy. Simple conservation of energy. Whatever comes in object 1 needs to go out the other side of object 1, needs to hit the object, my shield, needs to come off the other side of the shield, and needs to hit object 2. So I can write down that equation that we had between two objects, between object 1 and the shield. So that's this equation we had right here. So that's my heat transfer from 1 to S. Do the same thing from S to 2. So same equation, just different subscripts from shield and object 2. And again, those two heats need to be the same. If the emissivities of all three surfaces are the same, so if epsilon has the same value, these are all made from the same material, I can solve this, and what I end up with is that the temperature of my shield, Ts to the 4th, is exactly half of T1 to the 4th plus T2 to the 4th, so basically the average, not necessarily the average temperature, because these are both to the 4th power, but the average of the temperatures to the 4th power is the temperature of the middle guy. And so for that reason, I can again plug that back into these equations and get that my overall heat, just looking at the first and second object, is 1/2 sigma T1 to the 4th minus T2 to the 4th over this resistance term, 1 over epsilon 1 plus 1 over epsilon S minus 1. That should be epsilon 2. So I'm dealing with objects 1 and 2. Point of that. So what we saw is we put one shield in and we got exactly half of the radiative heat transfer. So putting that shield in, if this shield was not here, I wouldn't have this factor by half. And so by putting the shield there, I basically reduced the heat transfer by a factor 2. So just shove something in the middle and have exactly half the heat transfer. If you want even less heat transfer, shove more things in the middle. It can be shown that if you take more than one shield, you're going to reduce it by 1 over n plus 1. So in the previous case, I only had one shield, so I had 1/2 of the original heat transfer. If I have 3 shields like I have down here, that'll be 1/4. So each time you add an additional shield, you're not reducing it by the same factor. It gets less and less. But again, you are still reducing it. And this particular result, and the previous one before this, there was one big assumption we made, was that they all had the same value of epsilon, the same emissivity for all my surfaces. So this only holds if all the emissivities are the same. If I start putting things in here with different emissivities, it's going to be some other factor. It won't be exactly 1/n+1. So a couple examples. Have an example for the infinite surfaces, another example for the shields. So first up, the infinite plates. I have a horizontal pipe, 6 meters long, 12.5 centimeters in diameter, maintained at 150 degrees in a large room, with the walls of the room at 38 degrees Celsius. So again, basically I have this cylinder inside my room. I'm assuming I have this really, really large room around it. Epsilon 0.7 for the pipe. How much heat's lost through radiation by the pipe. So I know that, again, just dealing with 2 objects, sigma T1⁴ minus T2⁴ over these resistances. So getting off the cylinder, actually hitting the room, and being absorbed into the room. And then again, because the room's really large, F12 equals 1, so the pipe emits radiation. No matter where that radiation goes, it's eventually going to hit the room. A2 is also much bigger than A1, because again, my room is all the way around my pipe. So area there is much bigger. So using those approximations, to look at my previous equation here, I have 1/A2 essentially, but here I'm going to assume that A2 is really, really big. So that's just going to go to 0. F12 is going to be 1. I'm going to be left with an A1 there. And so there's my A1, there's my 0, because A2 is really, really big. And then this term coming off my cylinder. And so cleaning this up a bit, I get sigma T1⁴ minus T2⁴. And then this epsilon over epsilon A1 basically just cancel out this 1/A1. All I'm left with is this 1/epsilon 1A1. And because that's 1 over that, I can move it to the top. Sigma epsilon 1A1 T1⁴ minus T2⁴. This again was that shorthand equation we had from slide, where was it? Slide 5 or so. Yeah, so here's my slide right here. That equation is basically the one we're using. I just kind of proved it again. And so net heat transfer, sigma 5.67 times 10 to the -8 watts per meter squared, kelvins to the 4th. Epsilon was 0.7 for this guy. The area for my cylinder, pi times diameter times length. And then temperature of my pipe was 150. Again, want to make sure that's in Kelvin, so add 273. Temperature of the walls was 38. Again, make sure that's in kelvins. And I get a total heat transfer from radiation of 2,120 watts for this case. The second example, the one involving my radiation shields. I have 2 large parallel plates maintained at 400 and 600 degrees respectively. So this guy number 1 is at 400, this guy number 2 is at 600. They both have emissivities epsilon of 0.6. I want to reduce that heat transfer, so I'm going to put a radiation shield with epsilon of 0.1. So again, small epsilon, small emissivity, also means small absorptivity, means a lot of stuff is going to be reflected off this surface, so this is going to be a pretty good shield. Place equidistance between the plates, right in the middle. Want to calculate the radiant heat transfer through the plate shield arrangement per unit surface area. So Q/A is what I'm looking for in this case. Notice that in this case, I don't have the same epsilon, so this guy's 0.6, this guy's 0.6, but the shield is 0.1. So I can't simply use that 1/2 that we used before, because all my epsilons are different. So what I'm going to do instead is kind of set up my actual total thermal resistance per unit area. So I have a 1 minus epsilon 1 over epsilon 1. Usually it's epsilon 1A1, but because I'm dealing with per unit area for my heats, I can take the area out. So to get off surface 1, I have 1 minus epsilon 1 over epsilon 1. And then from that surface, I need to actually make it to the shield. So 1 over F1S, I'm going to call that guy from 1 to the shield, the view factor. have to be absorbed into the shield. So 1 minus epsilon s over epsilon s. That's on the left-hand side. Then coming out the right-hand side, have to make it off the shield. So 1 minus epsilon over epsilon s be emitted off the shield. And then from the shield, have to see object 2. So 1 over f2s. Technically, this should be f to s2, but infinite, so it's going to be the same thing. And then 1 minus epsilon 2 over epsilon 2 can be absorbed into object 2. That's my total thermal resistance for the system. So I actually calculate those values out. So I have 1 minus epsilon 1, which is 0.6 over 0.6. My view factor, F1S, is just 1. Then I have two things in the middle. So the first one being absorbed into the shield, and the second time being emitted off the shield. Both have the same value, epsilon and alpha, absorptivity, emissivity, both 0.1. So I phase out two of those for the middle part. And then F from the shield to 2, again, is a 1. And then be absorbed into object 2, emissivity of 0.6. So 1 minus 0.6 over 0.6. Grand total there is 21.33, my total resistance. And then simply heat flux, Q over A, sigma times T1 to the fourth minus T2 to the fourth over this total resistance. So 5.67 times 10 to the negative 8 watts per meter degree Celsius. Sorry, watts per meter squared, Kelvin to the fourth. 873 kelvins for my 600 degree surface number 1. 673 kelvins for my 400 degree Celsius surface number 2. Divided by this total resistance gives me a total radiative heat flux of 999 watts per square meter. So those are my two applications of these radiative heat transfer networks that we saw. It's nice, simple, one-dimensional ones again. Last class, we kind of introduced the three-dimensional version, so the three objects interacting with each other. We're going to go back to that next class, but next class we're also going to throw in some reflection in there, so things really get fun.